Welcome back, Geometry Scholars. Today's lesson is 1.3, Representing and Describing Transformations. Our essential question is, how can you use tools of the trade or concepts to describe the construction of geometric figures? And our objective today is that the student will be able to describe transformations using coordinate notation and perform transformations on a coordinate plane. So let's go ahead and get started with our vocabulary. A transformation is an operation that moves or changes a geometric figure in some way to produce a new figure. The original figure is called a preimage. The figure before the transformation is called a preimage. And then the new figure produced by the transformation is called the image. I know some of you might think it's crazy, though maybe the one before should be called the image and the new one the after image, but that's just not the case. The original figure is called the preimage, and the new figure is then called the image. A translation is a transformation that moves every point of a figure the same distance, in the same direction. Coordinate notation is one way to write a rule for a transformation. It uses an arrow to show how the transformations change the coordinates. And this right here is called prime notation. Prime notation. And we would call that piece I circled A prime. So it's called prime notation. Coordinate notation is one way to write a rule for a transformation. It uses an arrow to show how the transformations change the coordinates. Some transformations preserve length and angle measurements, and some do not. Rigid motion, or isometry, is a transformation that changes the location of a figure without changing the size or shape of the figure. So if it's simply moving places, then it's rigid. But if it's also becoming larger or smaller or becoming a different shape, then that would be called non-rigid. Translations and reflections and rotations, those are all rigid motions. The actual shape doesn't change, just the location or the position of the shape changes. A dilation would then be called a non-rigid motion or a non-rigid transformation because the shape and or the size does change. Okay? So think about rigid meaning staying the same, staying still. That's what a transformation is that doesn't really move its size or shape, it just moves its position. Whereas a dilation is non-rigid because its size or shape can change and does change. Let's move on to some examples. I'm going to do two of them with you, and then I'm going to have you try the third one on your own because I need to make sure that you are working and practicing these. So first up, we have a shape already on the coordinate plane. We have a triangle, and we need to find the original points. So I'm going to find A, B, and C. A is at 0, 4, and we should all be very comfortable with finding points on the coordinate plane. B is at 3, 0, and C is at 0, 0. And now I'm going to apply the transformation, A prime, and this is the only, I would say, new part, but it's not difficult. We apply the transformation, so we take the x coordinate and we're going to subtract 4. So the 0, the 3, and the 0, we're going to be subtracting 4 from that. So the A coordinate, the new one, A prime, is negative 4. B prime, the x coordinate, is negative 1. And C prime, the x coordinate, is also negative 4. And now we're going to find the y coordinate, and the y coordinate, we're going to be subtracting 3. So we'll be subtracting 3 from 4, 0, and 0. Okay? So the y coordinate for A prime is 1, for B prime is -3, and for C prime is also -3. And now that we've performed the translation, we're going to draw the new image. So I have -4, 1, -1, -3, and -4, -3. These are my new coordinates. I'm going to connect the points, and I have A prime, B prime, and C prime. Okay? And this particular transformation is called a translation. And it's called a translation because we only added or subtracted. So up here, the transformation that we applied was subtraction. So a translation is when we are going to add or subtract. Okay, and we can see that this particular shape moved to the left 4 spaces, and then it moved down 3 spaces. Okay, think about it. We subtracted 4 on the x from the x, so it moved to the left, and then we subtracted 3 from the y, so that's moving down. Okay, that's a translation. And these two figures are the same, so this is a rigid motion. They didn't change sizes, they just changed the position. Moving down to example B, we have xy, and we can see that some type of transformation was done to it. So let's go ahead and find our points. We have R, S, and T. R is at -4, 3. S is at -1, 3. And T is at -4, 1. I'm going to apply the transformation. And here, my coordinates are staying in the same exact place. The only thing that's happening is I'm changing the sign of the x coordinate. So I'm going to apply that negative sign. So R prime I'm applying a negative sign, so -4 becomes a +4. And my y coordinate's staying the same, so I'm just going to go ahead and finish that off. S prime, again, I'm applying a negative sign, so -1 becomes a +1. My y coordinate stays the same. And T prime, applying a negative symbol, becomes 4. My y coordinate stays the same. So here are all my all the coordinates of the image, and now I'm going to plot these points. R prime is 4, 3, 4, 3. That's R prime. S prime is 1, 3, and T prime is 4, 1. Connect your points. And now you have your image. And this particular transformation is called a reflection. Okay? It's called a reflection. The x changed sign. So x, the only thing that happened was that it changed the sign, and then the y stayed exactly the same. Nothing happened to the y. So it was reflecting across the y-axis. I had it on this side, and I reflected it across this side. So when the y stays the same and just the x sign changed, then I'm reflecting it across the y-axis. Now, if by chance the x would have stayed exactly the same and just the y sign would have changed, that would have been reflecting it across the x-axis. Okay? So this again is called a reflection, and it reflected across the y-axis. Okay, now we're going to move on to letter C. The first thing that I want you to do is I want you to find the coordinates of J, K, and L. Find the coordinates of J, K, and L. Okay, these are the coordinates of J, K, and L. Go ahead and check that you have the right ones. And then I want you to apply the transformation. The transformation is a 2xy, so the y coordinate is going to stay exactly the same. The 2x means you're going to multiply the x coordinate by 2. So I want you to go ahead and write the prime notation for J, K, and L. Okay, so these are the points for the prime notation. J prime is negative 2, 2, K prime is 4, 2, and L prime is 4, negative 4. Okay, and then I want you to go ahead and please plot these points now. As you can see, I plotted the points, and now I'm going to connect them. And I have my new shape. And this particular shape is called a dilation. And again, using our vocabulary from the beginning, this is a non-rigid transformation because it becomes bigger or smaller, but this one becomes bigger, and it involves multiplication. So when you see multiplication or division, then you know that you are working most likely with dilations. So this one is non-rigid, and it involved multiplication. Okay, so what I want you to do, please, is I want you to do example number 2 completely on your own. If you will see that I already have the pre-image and the image, so I want you to tell me what the rule was. I want you to tell me what the rule was. Take a second, look at it, see if you can figure out what the rule was. Hey guys, let me know if you actually got this right without having to see the answer first, because this is a really tricky one. The rule for this is that xy becomes negative yx, and this is a rotation, and rotations are definitely a little trickier. In rotations, and I'm actually going to write that word down here, it was a rotation, and not only was it a rotation, it was a 90-degree rotation. Okay, and I'm going to write some notes on the left-hand side that I want you to write down. In a 90-degree rotation, the xy becomes, sorry, draw my little arrow there, negative yx. In a 180-degree rotation, the xy becomes negative x, negative y. And in a 270-degree rotation, the xy becomes y, negative x. And don't worry, this is definitely tricky. It's new. We will be going over this more and more later on in the year, but I would definitely write these down, and you want to commit these to memory, because I have a feeling that you will, actually I should say I have a feeling, I know that you will see this all throughout the year and possibly on district and state exams. So you're going to want to know this information that I just wrote on the left-hand side. So in this particular instance, it was a 90-degree rotation. If you notice, the x and the y changed positions, and then the new x coordinate had a new sign. So the new x coordinate is then negative. Okay. Looking over here at the quadrants, we talked about a couple lessons ago about the quadrants and how this is quadrant 1, 2, 3, and 4. Okay. So if it's moving from one quadrant, if it's only changed into one quadrant, it's 90 degrees. If it's moved 2 quadrants, it's 180 degrees, and it's moved 3 quadrants, it's 270 degrees. So I'm not saying if it moves into quadrant 1, it's 90 degrees. I'm saying if it only moves from 1 to 2, or if it moves from 2 to 3, that's only a one quadrant move. But if it moves from 1 to 3, that's it's moved 2 quadrants, so that's 180 degrees. And if it moves from 1 to 4, then it's jumped 3 quadrants, that's 270 degrees. Okay, so rotations are definitely a little trickier, but they're honestly really easy once you get into them. So I knew this was a rotation because I noticed that I saw a lot of similarity between the numbers. So that I noticed, okay, um, this X was now the Y. It was in the Y spot. And my original Y is now, I'm sorry, my original Y is now in the X, but the sign was changed. Same thing here. My X is now in the Y spot, and my original Y is now in the X spot with the sign change. So what happened was the coordinates switched places, and then the new X coordinate, or the coordinate in the X position, is now negative. Okay, and again, please don't fret. We will be doing a lot of this in class. This was the hardest example. So if you've been understanding everything up through this, that's great. We'll keep doing this together. Just make sure that you are trying. Okay, example number 3. We're going to use coordinate notation to write the rules that maps each pre-image to its image, then confirm that the transformations is not a rigid motion. Again, a rigid motion means that it has stayed exactly the same. So we need to see if maybe a side has gotten longer, then it's no longer a rigid motion. So looking first, what our rule might be. Start off with X, Y. And so look first, did any of the X's change? 4 to 4, -2, -2, 0, 0. No, they did not. So X stayed exactly the same. And then look to see what happened to the Y's. The X's stayed the same. What happened to the Y's? The 1 became a 3, the -1 became a -3, and the -3 became a -9. So my first thought was, okay, well, 1 plus 2 is 3, but -1 plus 2 is not -3. So how else can I take a 1 and make it become a 3? Well, I can multiply it by 3. Well, -1 times 3 is -3, and -3 times 3 is -9. So that's what we did. The transformation is X, 3Y. So this is the rule. We're using coordinate notation. We wrote the rule. And so now we have to see if the transformation confirmed that it's not a rigid motion. And we do that by using the distance formula. We have to find if one side of the pre-image is equal to one side of the image. And if it is, then it's a rigid motion. If it's not a rigid motion. Okay? So I'm going to set up the distance formula. This is going to be obviously 0.1 and 0.2 for JK, and this is 0.1 and 0.2 for J prime, K prime. And setting up the distance formula for JK, if you remember the distance formula, is x2 minus x1 squared plus y2 minus y1 squared, and we take the square root of that sum. Okay? So I'm looking first at JK, square root of x2, so -2 minus 4 squared plus -1 minus 1 squared. So I have -6 squared plus -2 squared. 36 plus 4 is 40, the square root of 40. So JK, the length of JK was 40. And now I need to find out what the length of J prime, K prime, or JK prime is. And so I'm going to use those same points. Okay, I have -2 minus 4 squared plus -3 minus 3 squared. And again, notice I'm using, this was my x2, my x1, my y2, and my y1. And I'm using the distance formula, which we learned, or I should say reviewed, in a previous lesson. Okay, so -2 minus 4 is -6 squared plus negative 3 minus 3 is negative 6 squared. So I have 36 plus 36, 72. So J prime K prime is equal to the square root of 72. Are those the same? No, they are not the same. So the way that we want to word this is, since JK does not equal J prime K prime, the transformation is not rigid. If the sides were exactly the same, then we'd have to keep checking to see if all the sides were exactly the same. But since one side is not the same, we don't have to check the rest of them. Since one side is not the same, it is not rigid. Okay? So again, look at what I did. The first thing I had to do was I found the rule, and I said what was happening. And I can also tell that it's a dilation because it used multiplication. But then I did check the sides, and using the distance formula, I checked the length, the distance of JK, found it was the square root of 40. I checked the distance of J prime K prime, found that it was a square root of 72. Those two sides are not equal, so it's not a rigid motion. Okay? So what I'm going to have you do is I want you to go ahead and try example B. At least find the rule. What was happening here? How did the pre-image become the image? Okay, here's our rule. XY became 2x and half y. So negative 2 became negative 4. 4 became 8. Negative 2 became negative 4. You can see easily that that was being multiplied by 2. I know the y was a little trickier, but how does a 2 become 1? Subtracting, but then we have to apply that same subtraction to all of them, and 0 minus 1 is not still 0. So how else can 2 become 1? Well, we can divide it by 2. So it's half y, or 0.5 y is another way that you could say that. I like to say half y. Okay? So now that we have the rule, the directions said to confirm that it is not a rigid motion. So we have to check, see if the sides are the same. And I can tell by looking at it, since we are multiplying by a factor and dividing by a factor, that it's probably not a rigid motion. It looks like the size was changing, but we need to check. So again, I'm going to find the distance or the length of m and n, and I'm going to find the length of m prime, n prime. And this is going to be my x and y1. This is going to be my x and y2, and the same thing over here. So go ahead and set up the distance formula of mn, and I'm going to set up the formula for you, and then I want you to solve. So I'm looking, actually, let me erase this. I'm solving for mn. Mn is the square root of x2, which is 4, minus x1, which is negative 2. I'm going to square that, plus 0 minus 2 squared. Please go ahead and solve this problem. So mn equaled the square root of 40. So now we need to see what m prime, n prime equal. And again, I'll set up the distance formula and then please solve it. So we have 8 minus negative 4 squared plus 0 minus 2 squared. Go ahead and solve this problem. Okay, actually, sorry guys, this is 0 minus 1. Wrote the wrong number there. 0 minus 1. And again, I hope that you're catching my mistakes before I am. And if you were in class, you'd be telling me, Mrs. Locke, you made a mistake. And that would be quite fine because obviously I'm looking at a lot of numbers and I get confused. So go ahead and solve this problem. Okay, so the length of m prime, n prime is the square root of 145. So using the same language we used last time, since mn does not equal m prime, n prime, It's not rigid. Okay? If the lengths of the sides were the same, we'd have to then try the length of KL compared to, sorry, not KL. We'd have to then try the length of NP to N prime P prime, and then PM to P prime M prime. But since one of the sides is not rigid or not the same, we can then conclude that the whole thing is not rigid. Because in order for it to be rigid, all of the sides would then have to be the same. So if they were indeed the same, that's when we'd have to try other ones to see if they were all the same. Okay, hope that makes sense. And if not, ask me a question tomorrow. Okay, last one. I want you to go ahead and write the rule for this one and determine if it is a rigid motion or not. I'm going to have you guys do this one completely on your own. So I'm looking for a rule, and then I'm looking for you to determine if it is a rigid motion or not, and be able to tell me why or why not. Okay, so hopefully you took the opportunity to try to work this one out. The rule of this problem is that, the rule of this transformation, I should say, is xy became 3 over 2x, comma 3 over 2y. So I noticed that the numbers were going up. 2 became 3, 4 became 6, 2 became 3. But it just wasn't by adding, because 2 plus 1 is 3, but 4 plus 1 is not 6. So it was multiplying by something. But 2 times 2 is too large. So what it was multiplying by was 1.5, or 3 over 2. Because I can tell that if I take this 2 and I multiply it by 3 over 2, it becomes 6 over 2, which becomes the 3. And so that's how the 2 became the 3. And you can try that for all of them. You definitely have to become really skilled at looking for these patterns. So first of all, I wrote the rule, and then I needed to check to see if it was rigid or not rigid. So to do that, I found the distance of one side. So I used AB, the 2 comma 2, the 4 comma 2, and the length of AB was 2. And then I used A prime B prime, and the length of A prime B prime was 3. So since AB does not equal A prime B prime, it is not rigid. Okay? And lastly, you have a summary. Please write down something that we have learned today, a recap of today's lesson, and any problems or questions that you have. Again, I'm not expecting you to be experts on this, but I'm expecting you to try these problems, because when you come to class, as you know, we'll be working out problems, but I'm not reteaching the lesson. This is the lesson. It's just like me teaching it in class, but I'm teaching it via video tools instead. So please make sure you're trying your hardest, and I will see you next class.